So we begin with the fourth problem in this series, and this problem is problem number 1.320, and the problem is stating a bent tube is lowered into a water stream as shown in the figure. The velocity of the stream relative to the tube is 2.5 meter per second. The closed upper end of the tube is located at a height of 12 centimeter and has a small orifice. To what height h will the water jet spurt out? So we begin this problem by understanding the diagram which is given in the problem. So this is how the arrangement is made. So this is the velocity v which the problem is talking about, which is equal to 2.5 meter per second. And in the direction of this fluid flow, a bent tube is inserted which is containing an orifice, and due to which the fluid start rising up and spurt out at this point which from the small orifice and reaches a height h. So we are marking two positions, position 1 and position 2, between which we will be applying Bernoulli's expression. So over here, if we identify the reference level, so we can identify either the lowest point as the reference level or the surface of water as the reference level. So in this case, we are taking this one as the reference level. So h1 is equal to 0, and if I write h2, so h2 is equal to h0 plus h plus x above the reference level. So we are applying Bernoulli's equation between these 2 points. Again, important point to note over here is pressure at 2 is equal to atmospheric pressure, which is equal to P0. So if we apply the expression, so we can say applying Bernoulli's equation, so we can say P1 plus rho g h1 plus half rho v1 square equals P2 plus rho g h2 plus half rho v2 square. So if we calculate pressure at point 1, then pressure at point 1 is due to atmospheric pressure P0 and pressure due to liquid column of height x. So therefore we are writing pressure at 1 as P0 plus rho gx. Now since it is at the reference level, so we are marking this as 0, plus half rho v square, where v is velocity of flow. At 2, pressure is due to atmospheric pressure P0 plus rho g. h2 is equal to x plus h0 plus h. And at the highest point the velocity is 0. So this is the final expression that we have. Now if we solve this expression, then we can say P0 on both sides will be cancelled out. We get rho gx plus half rho v square equals rho g h0 plus rho g h plus rho gx. Again rho gx got eliminated and we have to calculate for h. So we are doing this calculation as half rho v square minus rho g h0 1 by rho g is equal to h. So this is the final answer that we have, and if we multiply by rho g, we get v square by 2g minus h0. So this is the final answer for this particular problem. Now if we substitute the values that we have, that is density being equal to 1000 kg per meter cube, g being 10 meter per second square, velocity of flow we are considering as 2.5 meter per second in the problem. So if we substitute the necessary values, then we get h equals 20 centimeter. So this is the final answer for this particular problem which we have discussed, problem number 1.320.